Welcome to Cranky Calculus, and we're here to go over limits using trigs, identities, and we're going to talk about the greatest integer function as well. These are things that we need to be pretty sharp at here, and hopefully your pre-calculus teacher went over what the greatest integer function is. If not, we will tackle that here today. So some trig limits that you need to be aware of here are if you have any type of form of sine of 0 over 0, that's going to equal 1. Anything in that form, sine of 0 over 0 or 0 over sine of 0, we're going to equal 1. And you can look at the trig limit box right there. That gives you everything you need to know. So for this first example here, we have the limit as x goes to 0 of sine of 7x over sine of 5x. If I plug in a 0, I'm going to get 0 over 0. That's not in the form of sine of 0 over 0 or 0 over sine 0. What I want to do here is I actually want to create those ratios. So I'm going to multiply the top by 7x, bottom by 7x, multiply the top by 5x, and bottom by 5x. You'll see where this is going in just a minute. I'm going to rewrite this limit to be sine of 7x all over 7x times 5x over sine of 5x. When I do that, I'm rearranging this so that I can have this be in the form of sine of 0 over 0 or 0 over sine 0. In doing so, I'm going to kind of come back up here and, okay, use the sine of 7x, use the 7x on the bottom, use the sine of 5x, use the 5x on top. That's leaving me with a remainder here of 7x over 5x. So the first factor here is going to equal 1. The second one's going to equal 1. And then the x's cancel out, giving me with 7/5, having a final answer here of 7/5. Going on to the second problem here. If we plug in a pi over 4 into the numerator, we're going to get 0. Denominator, same thing. We're going to end up with 0. We're going to have to use a little bit of trig identities here, nothing too fancy. A couple things I'm thinking about. Possibly my brain wanted to multiply by the conjugate here, but I'm going to end up with sine squared minus cosine squared, and that's going to end me up with nowhere. So why don't we just change this tangent into sine of x over cosine x. So I can rewrite this now as the limit as x goes to pi over 4 of 1 minus sine of x over cosine x all over sine x minus cosine x. Now the whole reason I'm going to do this right now is that I can actually, since I have a fraction inside of a fraction here, here's a math trick that my teacher taught me many years ago. If you have a fraction in a fraction, multiply every term by that denominator. So I multiply that sine over cosine by cosine x, multiply this 1 by cosine x, and multiply this entire bottom here by cosine x. Okay? When you do that, the top actually gives us something we can cancel out. I'm going to leave everything in the bottom as factors. So the top is going to give me cosine of x minus sine of x all over sine x minus cosine x. And then times that cosine on the bottom. Now, since I'm doing that, you can notice here I have a cosine minus sine on top and sine minus cosine on bottom, which means that I can multiply one of these by -1. So if I multiply the top here by -1, I have to even that out with the bottom. Then I have factors that can cancel out, and that's going to leave me with a negative on top. So I'm going to get -1 over cosine of x. Because I need to multiply that by -1, which is going to cancel out this -1 right here. I'll highlight in black. That's going to cancel out, and that's going to flip the signs of the sine and the cosine. So that's why that cancels out, leaving with a -1. On the bottom, I'll just throw it up top, just make it easier. I can now plug in my pi over 4, -1 over cosine of pi over 4, which hopefully you know that is the same thing as secant of pi over 4, negative secant of pi over 4, which is actually negative root 2. Let's go ahead and talk about this greatest integer function in case you've never seen it before. Maybe you've seen some parts with the greatest integer function. before. Hopefully this graph looks a little familiar with you. The greatest integer function is just when we round down to the left. So 3.1 becomes 3, 3.9 becomes 3. So we're always going down. Be careful with negatives. Negative 3.1 is negative 4. So it gets a little tricky when we get to limits. So let's just evaluate this one right here. Looking at 1 to the left of the greatest integer function of x plus 1 all over x plus 1. Now, since I'm evaluating to the left, I'm actually looking at x equals 0.99999, really as close to 1 as I can get on the left-hand side. And as I do that, this is going to be 1.99999 all over 1.99999, which you would think is 1, but this is the greatest integer function. Those extra bars there. That's going to round down to 1 over 1.9999. And really, I can plug in numbers even closer to 1 as we keep going and going. So the top is going to equal 1, and if I plug in numbers super close to 1, it's going to give me a 2. That is why this question is equal to 1 over 2. The top is going to stay on the left-hand side. It's going to stay as a 1 no matter what, and the bottom will be able to be pushed up to be a 2. And that's going to wrap up our video here. Do not forget to like and subscribe.